The nearest known planet beyond our solar system lies just over 4 light-years away, remarkably close by cosmic standards. It carries a mass similar to Earth and travels within the habitable zone of its star, where conditions might allow liquid water to exist. When scientists revealed its discovery in 2016, many headlines quickly labeled it as our closest second Earth. But those headlines left out something essential. We have never directly observed this world. We do not know if it possesses an atmosphere, and we have no evidence that liquid water has ever remained on its surface, even briefly. The star it orbits is far from gentle. It is one of the most unstable stars in our local region of space, releasing bursts of radiation that can be hundreds of times more intense than anything produced by our Sun. In that sense, Proxima B may not represent our nearest hope, but something far more uncertain, perhaps even our nearest disappointment. If you enjoy these quiet explorations into the deeper realities of the universe, you might consider subscribing. It simply allows more of these stories to continue. Now, let's dive in. Every civilization that has ever looked up into the night sky has asked a similar question. Is there another world out there, somewhere, that resembles our own? For most of human history, this question belonged to philosophy. Later, it became the domain of science fiction. Then, beginning in the 1990s, it quietly entered the realm of real science. Astronomers started detecting planets around distant stars. At first, they found massive worlds, gas giants orbiting extremely close to their stars, heated to extreme temperatures. Then came smaller planets, rocky surfaces, and worlds positioned within habitable zones where liquid water might, in principle, exist. With each discovery, the question felt closer to an answer. But every one of these worlds carried the same unavoidable limitation. They were distant, not just far, but unimaginably far. Hundreds of light years, thousands, tens of thousands. Distances so vast that even light, the fastest thing allowed by the universe, would take centuries or even millennia to cross them. You could imagine finding a perfect twin of Earth, a world filled with oceans and unfamiliar ecosystems, and it would still remain unreachable if it lay 4,000 light-years away. No spacecraft we could build would ever arrive. No telescope we could construct would reveal its surface in detail. No message we could send would return within the lifetime of our civilization. The search for another Earth has always carried this quiet limitation. The universe is vast, and distance quietly removes everything from reach. Then, on August 24th, 2016, something changed. A group of 31 scientists, led by Guillaume Anglada Escudé at Queen Mary University of London, announced the discovery of a planet orbiting Proxima Centauri, the closest star to our Sun. This world was not thousands of light-years away. It was just over 4 light-years from Earth. Not 4,000, not 400, just over 4. In cosmic terms, that distance is almost negligible. It is the astronomical equivalent of a nearby neighbor. It is close enough that the light reaching us from Proxima Centauri tonight began its journey only a few years ago. Close enough that engineers began outlining possible. Close enough that for the first time in human history, the idea of another habitable world no longer felt abstract, but immediate and personal. This planet became known as Proxima Centauri B, and at first glance, everything about its discovery seemed almost too well aligned. To understand why Proxima B captured so much attention, we need to look more closely at the star it orbits. Proxima Centauri is not just another nearby star. It is the closest star to our solar system, and part of a 3-star system known as Alpha Centauri, a system that has drawn the attention of astronomers for generations. Alpha Centauri A and Alpha Centauri B form a bright binary system, 2 stars not unlike our Sun, bound together in a shared orbit with an average separation of about 23 astronomical units. They are visible from the southern hemisphere of Earth, contributing to one of the brightest points in the night sky. Yet far beyond this luminous pair, at a distance of roughly 13,000 astronomical units, lies a much dimmer companion, Proxima Centauri. a small red dwarf star. Often described as the smallest member of the family, red dwarfs are in fact the most common stars in the Milky Way, making up around 70% of all stars in our galaxy. They are smaller, cooler, and far less luminous than stars like our Sun. Proxima Centauri contains only about 12% of the Sun's mass and around 14% of its radius. Its surface temperature is close to 3050 Kelvin, compared to nearly 5800 Kelvin for the Sun. In visible light, its brightness is almost negligible. It emits only about 0.0056% of the Sun's luminosity, which means our star shines roughly 18,000 times brighter. Because of this, Proxima Centauri remains invisible to the naked eye, despite being the closest star to Earth, even under the darkest and clearest skies. Scanning the constellation of Centaurus would reveal nothing of it without a telescope. The stars that do stand out in that region are often hundreds of light years farther away, yet appear brighter simply because they emit far more light. In this way, Proxima Centauri remains hidden in plain sight, closer than any other star, yet too faint for us to see directly. And within the broader Alpha Centauri system, this faint companion makes its surrounding planetary environment especially intriguing. Alpha Centauri A, the brightest member of the system, is a G-type star strikingly similar to our Sun. It holds a little more than 1 solar mass, with a surface temperature near 5800 Kelvin, and shines with roughly 50% more luminosity than our star. Alpha Centauri B, by comparison, is slightly smaller and cooler, a K-type star with about 90% of the Sun's mass. Together, these two stars orbit one another over a period of roughly 80 years, sometimes drawing as close as 11 astronomical units, and at other times drifting out to around 36. For many years, astronomers searched this bright pair for signs of orbiting planets, often with disappointing results. In 2012, a team reported the possible detection of an Earth-mass planet around Alpha Centauri B, a discovery that quickly gained global attention. But further analysis suggested that the signal was not planetary at all, instead arising from subtle effects in the data itself. The proposed planet effectively disappeared. The Alpha Centauri system began to feel almost elusive, offering promising signals only to withdraw them, as if remaining just beyond the reach of certainty. That sense of uncertainty continued in a striking way in 2025, when a team working with the James Webb Space Telescope reported compelling evidence of a giant planet orbiting Alpha Centauri A, possibly within or near its habitable zone. The initial signal came from observations in August 2024, using a coronagraph to block out the overwhelming light of the star. What they detected was an object more than 10,000 times fainter than the star itself, positioned at a distance roughly twice that between Earth and the Sun. It was an exciting result. But when astronomers returned to observe the same region in February and April of 2025, the object was no longer visible. The researchers described it as a disappearing planet and began running simulations across millions of possible orbital paths to understand this behavior. One explanation remained consistent with the data, that the object could indeed be a real planet, moving along an orbit that periodically carries it into and out of view. Depending on its position and the limits of the observing setup, if this interpretation is correct, it would suggest that the nearest Sun-like star to Earth hosts a giant planet within its habitable zone. But for now, that conclusion remains uncertain. The Alpha Centauri system, our closest stellar neighbor, continues to offer possibilities that sit just beyond clear confirmation. Among all these uncertainties, Proxima B stands apart as the one planet whose existence is firmly established. That certainty gives it a unique emotional weight. In a system filled with ambiguity, Proxima B is real. And this combination of proximity and detectability made Proxima Centauri an especially compelling target for planet hunters. Red dwarf stars offer a particular advantage in this search. Because of their small size and low mass, even a relatively small planet can exert a noticeable gravitational influence. The resulting motion of the star A subtle back-and-forth wobble becomes easier to detect. An Earth-mass planet orbiting a star like our Sun produces an almost imperceptible shift, on the order of just a few centimeters per second. That is beyond what current instruments can reliably measure. But around a red dwarf like Proxima Centauri, a similar planet creates a larger effect. A wobble of roughly 1.4 meters per second, still extremely small, but just within the limits of our most precise instruments. For years before its official discovery, astronomers had been searching for planets around Proxima Centauri. Studies in 2008 and 2009 ruled out larger planets within the habitable zone. Yet subtle hints continue to appear in earlier data. In 2013, Mikko Tuomi at the University of Hertfordshire identified signals in archived observations that suggested something might be there. This prompted the European Southern Observatory to take a more direct approach. In January 2016, they launched a focused observing campaign known as Pale Red Dot, a name inspired by Carl Sagan's well-known reflection on Earth as a pale blue dot. The objective was simple, but demanding: to observe Proxima Centauri night after night, using the most precise instruments available, and search for the faint repeating signal of an orbiting planet. The approach was methodical: measure the star's radial velocity with extreme precision, and search for a repeating motion, a subtle, rhythmic shift that might reveal the presence of an unseen companion. Two instruments carried most of this effort: HARPS, the High-Accuracy Radial Velocity Planet Searcher, installed on the 3.6-meter telescope at La Silla in Chile, and UVSR, the Ultraviolet and Visual Echelle Spectrograph, operating on the 8-meter Very Large Telescope at Paranal. Both systems analyze starlight at remarkable levels of detail. They break incoming light into its component wavelengths, then track minute changes in spectral lines caused by the Doppler effect. When a star moves slightly toward Earth, its light shifts toward blue. When it moves away, the light shifts toward red. If a planet is orbiting, it pulls the star back and forth in a steady cycle, leaving behind a smooth, wave-like pattern in the data. Identify that pattern, determine its timing, and from that, estimate the planet's mass. This is how astronomers detect a world they cannot see. The Pale Red Dot campaign revealed exactly such a signal, clear and consistent, repeating every 11.2 Earth days. The size of the star's motion matched what would be expected from a planet with a minimum mass close to that of Earth. This orbital period also implied a distance of about 0.048 astronomical units from the star. Crucially, that distance places the planet within Proxima Centauri's habitable, the region where incoming stellar energy could, under the right conditions, allow liquid water to exist on a surface. The probability that this signal was a false detection was estimated to be less than 1 in 10 million, and the findings were published in Nature. The conclusion was clear: the planet was real. What followed were headlines filled with excitement. The nearest potentially habitable world. An Earth-like planet next door. A second Earth only a few light years away. The language reflected the sense of possibility, and perhaps also the sense of urgency. By that time, astronomers had already confirmed thousands of exoplanets over the course of 2 decades, but all of them were distant, far beyond any realistic reach. Proxima B stood apart. A distance of just over 4 light-years is still immense by human standards. Light itself takes more than 4 years to travel that span. A spacecraft moving at speeds similar to the Voyager probes would require over 70,000 years to arrive. And yet, for the first time, the idea of reaching another star system began to feel less abstract. Researchers and engineers started to consider whether such a journey could be achieved within a human lifetime. One proposal, known as the Breakthrough Starshot Initiative, supported by Stephen Hawking and investor Yuri Milner, outlined a bold concept: thousands of extremely small spacecraft, each only a few grams in mass, could be attached to ultra-thin light sails and accelerated to a significant fraction of the speed of light using a powerful laser array based on Earth, at around 20% of light speed. Such probes could reach the Alpha Centauri system in roughly 20 years, adding the time required for signals to return. Data from Proxima Centauri might arrive within a single human generation. It is an elegant idea, but one that comes with formidable engineering challenges. No one had ever constructed a laser system powerful enough for such a task. No one had created a sail thin and resilient enough to survive that level of acceleration. And no one had solved the challenge of guiding a probe weighing only a few grams across more than 4 light-years with the precision required to pass a planet. Yet the fact that these ideas were being taken seriously reveals something deeper about Proxima B. This was no longer a distant world reserved for future generations to imagine. It was a planet that, in some sense, felt within reach, part of our own time. Part of what made its discovery so compelling was how neatly the system seemed arranged. The habitable zone around Proxima Centauri lies much closer to the star than Earth's does to the Sun. Because the star emits so little energy, any planet must orbit at a close distance to receive enough warmth. The inner boundary of this zone sits at about 0.023 astronomical units, while the outer edge extends to roughly 0.054. Proxima B travels near the middle of this region, at around 0.048 astronomical units. By comparison, Mercury orbits our Sun at approximately 0.39 astronomical units. So despite being more than 8 times closer to its star than Mercury is to ours, Proxima B receives only around 65 to 70% of the energy that Earth receives from the Sun. In terms of total energy, this places it somewhere between Earth and Mars. Mars, for example, receives a little under half of the sunlight that reaches Earth. From this perspective, the idea of liquid water on Proxima B does not seem unreasonable, at least under the right atmospheric condition. The estimated mass of the planet added further interest. The radial velocity method provides only a minimum mass, not the exact value, because it measures motion along our line of sight. If the planet's orbit is tilted, the true mass could be somewhat higher. Initial estimates in 2016 suggested a minimum mass of about 1.3 times that of Earth, already an intriguing result. Then, in 2020, improved measurements from the espresso spectrograph indicated a slightly lower value. The planet appeared to be only about 17% more massive than Earth, bringing it even closer to our own world in scale. More recently, in 2025, a new instrument known as NIRPS, operating in the infrared at La Silla, provided the most precise measurements so far. The minimum mass was determined to be about 1.055 Earth masses, with only a small margin of uncertainty. Within those limits, Proxima B is almost indistinguishable from Earth in mass, at least based on what we can currently measure. If we assume an orbital inclination of about 47 degrees, consistent with the estimated rotation axis of Proxima Centauri, the planet's true mass would be closer to 1.4 times that of Earth. Even then, it remains well within the range that scientists classify as a rocky, terrestrial world. The NIRPS results, released in July 2025, were part of the instrument's first scientific outputs and marked an important step forward. For the first time, astronomers were able to measure the radial velocity of a red dwarf star in the near-infrared with a precision better than 1 meter per second. Alongside refining Proxima B, the data also confirmed the presence of Proxima D, a much smaller planet first identified in 2022. With a minimum mass of about 0.26 Earth masses and an orbital period of just over 5 days. Proxima D is now among the least massive exoplanets ever detected using this method. At the same time, the earlier claim of a third planet, Proxima D, has not held up. This object, once thought to be a super-Earth on a wide orbit of roughly 5 years, could not be confirmed in the new data. The signal appears to be uncertain, possibly the result of stellar activity rather than a true planetary companion, a conclusion that aligns with previous studies questioning its existence. At present, the Proxima Centauri system seems to host 2 confirmed planets. One is Proxima B, similar in mass to Earth and located within the habitable zone. The other is the much smaller Proxima D, orbiting closer to the star. The significance of this arrangement is difficult to overstate. For decades, astronomers had hoped to find a potentially habitable world close enough for detailed study, and when it finally happened, it appeared at the very first star beyond our Sun. Not the 10th nearest, not the 50th, the very first. It is almost like setting out across an ocean in search of distant land, only to discover an island already visible from the shore. That sense of proximity shaped how Proxima B was perceived from the beginning. It became more than just a scientific result. It entered culture, appearing in stories, research proposals, and public imagination. It began to represent something larger, the possibility that the universe might be more accommodating than we once believed. And if the nearest star hosts a planet in its habitable zone, it raises a deeper question. What does that imply about the countless red dwarfs spread across the galaxy? From a statistical perspective, it suggests that such worlds may be surprisingly common. Perhaps 1 in 5 red dwarfs hosts a planet within the habitable zone, or perhaps even more. In that sense, Proxima B is not just a single discovery, but a clue about the broader structure of our galaxy. It suggested something profound, that Earth-sized worlds in stable, temperate orbits may be far more widespread than we once imagined. The statistical implications are worth exploring, because they begin to reshape our view of the galaxy itself. Red dwarf stars make up about 70% of all stars in the Milky Way. Current estimates place the total number of stars in our galaxy somewhere between 200 billion and 400 billion. That would imply there are roughly 140 billion to 280 billion red dwarfs alone. Observations from the Kepler mission, along with ground-based radial velocity surveys, indicate that somewhere between 1 in 4 and 1 in 5 of these stars may host a rocky planet within the habitable zone. Even if we take the more conservative estimate, the numbers become striking. That leads to something like 30 to 50 billion potentially habitable rocky planets orbiting red dwarfs in our galaxy. 50 billion. A number that quietly exceeds the total human population on Earth many times over. Each of these worlds exists in a region where liquid water could, in principle, be stable. Each might possess an atmosphere, a surface, perhaps even a climate system of its own. The fact that Proxima B was found at the very first red dwarf system studied with sufficient precision raises an important question. Was this simply an extraordinary coincidence? Or does it suggest that such planets are genuinely common? If habitable zone worlds around red dwarfs were rare, discovering one at the nearest star would be extremely unlikely. The fact that it appeared immediately hints that the higher estimates may be closer to reality. This idea is both exciting and slightly disorienting. It suggests that we live in a galaxy filled with potentially habitable environments. Worlds capable of supporting liquid water are not rare exceptions hidden in distant regions. They may be widespread, orbiting the most common type of star. Within the most common kind of stellar system, the Milky Way may not be a sparse landscape with occasional pockets of habitability. It may be something closer to an ocean of possibilities, stretching from our nearest neighbor to the outermost spiral arms we can observe. But abundance is not the same as accessibility. And more importantly, the presence of a habitable zone does not guarantee a habitable world. As the story of Proxima B continues, this distinction becomes increasingly important. Because everything we have described so far, its mass, isobi, its position within the habitable zone, and its proximity to Earth, all of these are well-supported observations, confirmed across multiple instruments and years of data. Nothing here is exaggerated. The issue is not that the data is incorrect. The issue lies in what the data does not tell us. When the Pale Red Dot team presented Proxima B, they chose their words with great care. The paper described a planet with a minimum mass close to Earth's, orbiting within the habitable zone of its star. It did not suggest that the planet was habitable. It did not state that the planet possessed an atmosphere. It did not indicate that liquid water existed on its surface. In fact, it made no claims at all about surface conditions. The discovery itself was based purely on radial velocity measurements. It confirmed that a planet is present and defined its orbit, nothing more. Yet the public narrative quickly moved beyond what the science actually showed. The term habitable zone became interpreted as habitable. Earth mass was taken to mean Earth-like. Nearest star began to feel almost reachable. Each shift in meaning was subtle, each one understandable, and each one misleading, because a habitable zone is not a promise of habitability. It is simply a thermodynamic boundary. A planet within this region receives an amount of energy that could allow liquid water to exist, but only if it has the right kind of atmosphere. And that assumption carries the entire conclusion, despite having no direct evidence. We do not know whether Proxima B has an atmosphere. There is no spectroscopic measurement of its air. We do not know if it has a magnetic field strong enough to protect that atmosphere from stellar radiation. We do not know if liquid water has ever existed there. We do not know the nature of its surface, its climate, or whether it shares any real similarity with Earth. The planet was discovered through a tiny shift in starlight. That motion reveals its presence, its orbital speed, and an estimate of its mass. Beyond that, it tells us very little about what the planet truly is. This divide between detection and understanding defines Proxima B. It is perhaps the most emotionally compelling exoplanet ever found, and at the same time, one of the least understood. And the reason for this is not a lack of effort or resources. It arises from geometry, from physics, and from the nature of the star it orbits. What follows will challenge many of the assumptions surrounding this world. It will show why even the most basic properties, such as its size, its density, or the composition of its atmosphere, remain beyond our reach. And it will reveal how a single geometric detail of its orbit has placed some of the most important questions in exoplanet science just out of reach of current technology. There exists a technique in astronomy so powerful that it has allowed scientists to study the atmospheres of planets hundreds of light years away. Using it, they have identified water vapor, carbon dioxide, methane, and even sodium in the skies of distant worlds. It has even allowed scientists to estimate temperatures, wind patterns, and cloud structures on worlds that no human eye will ever directly observe. This method is known as transmission spectroscopy, and it works through a principle that is both simple and remarkably precise. When a planet passes in front of its star, a small portion of the starlight travels through the planet's atmosphere before reaching our instruments. Different molecules absorb specific wavelengths of that light. By comparing the star's spectrum during this event with its spectrum at other times, astronomers can determine which molecules are present in the atmosphere. It is somewhat like holding a glass of tinted liquid up to a light source. The color reveals what is mixed within it. In the same way, the spectrum reveals what exists in the air of a distant world. Transmission spectroscopy has become one of the most powerful tools in the study of exoplanets. The James Webb Space Telescope relies on it regularly. Ground-based observatories also apply it when conditions allow. It has reshaped our understanding of gas giants, smaller Neptune-like planets, and even some rocky worlds orbiting distant stars. In principle, it is the exact method we would use to determine whether Proxima B has an atmosphere, what that atmosphere contains, and whether it includes gases that might be linked to biological processes. It is the technique that could transform Proxima B from a distant signal into a well-understood world. And yet, it is the one method we cannot apply in this case. Proxima B does not pass in front of its star from our point of view. This single geometric detail defines both what we know and what remains hidden about the closest known exoplanet. A transit occurs when a planet moves directly between its star and our line of sight. From Earth, the planet briefly crosses the face of the star, blocking a small fraction of its light. This slight dimming can be measured. The depth of the dip reveals the planet's size, the timing reveals its orbit, and the filtered light carries information about its atmosphere. But such alignments only occur when the orbit is oriented at just the right angle relative to our perspective. For a planet at Proxima B's distance from its star, the chance of this alignment is only about 1.5%. In other words, the odds were never in our favor. Still, Astronomers searched carefully. The possibility was too important to ignore. The original discovery paper in 2016 reported no signs of transits in the available data. In the following year, observations using the MOST space telescope monitored Proxima Centauri for more than 40 days and identified 2 possible signals. However, the star's frequent flaring introduced significant noise, and the uncertainty remained high, with a false negative rate estimated between 20 and 40%. In the end, no confirmed transit was found. Follow-up observations from ground-based campaigns, including those at Las Campanas Observatory, gathered hundreds of data points and still found no evidence of a transit. Then the Transiting Exoplanet Survey Satellite, known as TESS, observed Proxima Centauri across multiple sectors using rapid, high-precision measurements taken every 2 minutes. To improve sensitivity, the TESS team applied advanced flare modeling techniques, allowing them to detect planets as small as about 0.4 times Earth's radius. The conclusion, however, was clear. There is no transit. Proxima B does not pass in front of its star from our point of view. The opportunity to use transmission spectroscopy is effectively closed. This limitation is more significant than it may first appear. Without a transit, we cannot determine the planet's radius. Radial velocity measurements provide mass, or more accurately, a minimum mass. This is because the method only captures motion along our line of sight. The true mass depends on the inclination of the orbit, the angle at which it is tilted relative to us. If the system is viewed nearly edge-on, the measured signal is close to the full value. If the orbit is more inclined, the actual mass could be considerably larger. For Proxima B, the minimum estimate is close to 1 Earth mass, but this is not a precise value. It is a lower limit. The true mass could be somewhat higher, potentially approaching 1.5 times that of Earth, depending on the unknown orbital angle. In either case, it likely remains a terrestrial world, but the uncertainty is meaningful. Without knowing the inclination, we cannot determine the exact mass, and without a measured radius, we cannot calculate density. Density is crucial, because it reveals composition. It tells us whether a planet is dominated by rock and iron, like Earth, or contains large amounts of ice, or perhaps a thick volatile envelope. A planet with around 1.4 Earth masses could be a dense, metal-rich world, slightly smaller than Earth, or it could be rich in water, with a deep global ocean, or it could be a rocky core surrounded by a substantial atmosphere. Mass alone cannot distinguish between these very different possibilities. In practical terms, this creates a sharp contrast. For planets that transit their stars, astronomers can measure mass, radius, and density, and even analyze atmospheric composition. With that information, they can build detailed models of internal structure, surface conditions, climate systems, and even search for potential biosignatures. For Proxima B, we have only a minimum mass and an orbital period. Everything else comes from models. Everything else depends on assumptions. These models are sophisticated and valuable, and many research teams have explored a wide range of scenarios. Some assume the planet is tidally locked, always showing the same face to its star. Others consider resonances similar to Mercury's orbit around the Sun. Different simulations test Earth-like atmospheres, carbon dioxide-dominated environments, thin or thick atmospheres, or none at all. They imagine worlds covered entirely by oceans, planets with scattered landmasses, frozen surfaces locked in global ice, or environments driven into extreme greenhouse conditions. Some simulations suggest climates where liquid water could remain stable. Others point toward extreme, hostile environments, and some describe worlds locked in deep, global freeze. The range of possible outcomes is vast, because the range of assumptions behind them is equally vast. Each model shows what Proxima B might be under a specific set of conditions, but none of them reveal what the planet actually is. This is not a flaw in the modeling itself. Climate simulations of exoplanets represent some of the most careful and creative work in planetary science. Researchers are clear about their assumptions and transparent about the limits of their result. The difficulty lies elsewhere. Models depend on constraints, and in the case of Proxima B, those constraints are extremely limited. When scientists simulate Earth's climate, they rely on detailed measurement, atmospheric composition, surface pressure, ocean coverage, reflectivity, incoming solar energy, and a known rotation rate. For Proxima B, the inputs are far more limited, mainly an estimate of stellar energy and a minimum planetary mass. This leaves a wide gap in our understanding. The models attempt to fill that gap with assumptions, and different assumptions lead to entirely different outcomes. Somewhere within this wide range of possibilities lies the real Proxima B, but at present, we have no way to identify where. Even the concept of the habitable zone deserves closer examination. When astronomers describe a planet as being in this zone, they mean it orbits at a distance where incoming stellar energy could allow liquid water to exist. Given certain atmospheric conditions, traditional models assume an atmosphere similar to Earth's, with water vapor and carbon dioxide acting as greenhouse gases. Under these assumptions, the inner edge of the zone marks where a runaway greenhouse effect would evaporate all surface water, while the outer edge marks where carbon dioxide would condense and temperatures would fall below freezing, regardless of atmospheric warming. For Proxima Centauri, this region extends from about 0.023 to 0.054 astronomical units, and Proxima B lies well within this range. This is a meaningful observation. It indicates that the planet receives a level of energy broadly consistent with the possibility of liquid water, but being in the habitable zone does not guarantee that a planet is habitable. It is only a necessary condition, not a sufficient one. Venus, for example, lies near the inner edge of our Sun's habitable zone, yet its surface temperature exceeds 460 degrees Celsius under a dense carbon dioxide atmosphere. Mars, near the outer edge, has a surface pressure less than 1% of Earth's, with average temperatures around -60 degrees Celsius. Both exist near the habitable zone, yet neither supports life as we know it. Earth's habitability depends on far more than distance from the Sun. It relies on a precise combination of factors: an atmosphere with the right composition and pressure, a magnetic field that shields it from solar radiation, active plate tectonics that regulate carbon over long timescales, and a relatively stable rotational axis influenced by the Moon. Remove any one of these elements, and Earth itself might no longer be a habitable world. Add those same conditions to a different planet, and it might become habitable regardless of its exact distance from its star. The habitable zone simply indicates where liquid water could exist from a thermodynamic perspective. It does not tell us whether water is actually present. It does not tell us whether the planet can retain an atmosphere under constant stellar radiation. It does not reveal anything about surface geology, magnetic protection, volcanic activity, or any of the many other factors that shape whether a world can truly support life. For Proxima B, being in the habitable zone is only the starting point of the question, not the conclusion. This nuance is often lost as information moves from scientific papers to public interpretation. Researchers are careful in their wording. Press releases are less precise. Headlines tend to simplify even further. By the time the idea reaches a wider audience, a planet in the habitable zone is often described as a habitable world, or even an Earth-like twin. Proxima B has experienced this shift more than most, largely because of how close it is. A planet in the habitable zone, 4,000 light-years away, remains an interesting data point. A similar planet just over 4 light-years away begins to feel like a destination. That sense of proximity changes the language, and the language shapes how the discovery is understood. There is also a more subtle complication in the data, one that is rarely discussed outside specialist circles. Measuring radial velocity around red dwarf stars is especially challenging, because these stars are inherently active and variable. Proxima Centauri, in particular, is a flare star with strong magnetic activity. Its surface is marked by star spots, similar to sunspots but often more intense. As the star rotates, these features create repeating signals in the spectral data, signals that can resemble or interfere with those caused by orbiting planets. In addition, magnetic activity alters the shape of spectral lines, introducing shifts that are unrelated to planetary motion. Separating a genuine planetary signal from this background noise is one of the most demanding tasks in observational astronomy. The Pale Red Dot team approached this problem with great care. They determined that Proxima Centauri rotates roughly once every 83 days, a period that does not match the 11.2-day signal attributed to the planet, nor is it a simple multiple of it. This difference strengthens the case that the signal is planetary in origin. They also examined indicators of stellar activity and found no correlation with the 11-day cycle. Further supporting the detection, the 2025 NIRPS data provided further confirmation, detecting Proxima B clearly in the near-infrared, a region where stellar activity behaves differently than in visible light. The agreement across multiple instruments, different wavelength ranges, and observations collected over nearly a decade leaves very little doubt. Proxima B is real. But the case of Proxima C shows how uncertain this field can be. In 2020, researchers reported evidence for another planet in the system, a so-called super-Earth with a minimum mass of about 5.8 times that of Earth, orbiting with a period of just over 5 years. The signal appeared in data from HARPS and UVs, and even received tentative support from measurements made by the Hubble Space Telescope. If confirmed, Proxima C would have been among the coldest exoplanets ever detected. Yet a reanalysis in 2022 cast doubt on the finding, suggesting the signal could be explained by systematic effects within the data. When the NIRPS team examined more than 400 high-resolution spectra of Proxima Centauri in 2025, they found no clear confirmation. There were faint indications of a possible signal at a slightly different period, but nothing strong enough to be considered definitive. As a result, Proxima C remains unconfirmed and is now widely regarded as uncertain. This is a reminder of how delicate these detections can be. A planet that appeared in peer-reviewed studies, supported by space-based measurements, and discussed extensively in the scientific community, may not exist at all. In comparison, the detection of Proxima B is far more secure. Its signal is stronger, its orbital period is shorter. The dataset spans many years, and the agreement between instruments is consistent. Even so, the Proxima C episode highlights an important point. When astronomers are measuring stellar motions on the order of 1 or 2 meters per second, within a background shaped by magnetic activity and instrumental limits, the boundary between a real planet and a false signal can become surprisingly narrow. The same 2025 observations also confirmed Proxima D, a much smaller world first suggested in 2022. This planet has a minimum mass of about 0.26 Earth masses, making it only slightly more massive than Mars. And it completes an orbit in just over 5 days, much closer to the star than Proxima B. Its existence was initially uncertain, but the NIRPS data independently recovered the signal and combined it with HARPS observations to establish a reliable detection. Proxima D is now the least massive planet in the system, confirmed by 2 independent instruments. Yet, like Proxima B, it has only been detected through radial velocity. There is no transit, no measurement of its size, and no information about its atmosphere. We know that it exists. We have an estimate of its mass. We know its orbit. Beyond that, we are still inferring. So it is worth pausing here to consider what we truly know about the closest known exoplanet to Earth. We know that Proxima B exists, confirmed by multiple instruments over nearly a decade of observations. We know its orbital period is about 11.2 days. We know it orbits at a distance of roughly 0.048 astronomical units. We know its minimum mass is close to 1.055 times that of Earth. We also know that it lies within the habitable zone of Proxima Centauri. We know that it does not transit its star from our point of view. and that it has not been directly imaged. But beyond these points, our knowledge becomes far more limited. We do not know its radius. We do not know its density. We do not know whether it is primarily rocky, ether, or something in between. We do not know if it has an atmosphere, and if it does, we do not know its composition, its thickness, or whether it can remain stable over time. We do not know if the planet possesses a magnetic field. We do not know its rotation rate. Although it is likely influenced by tidal forces, we do not know if water exists there in any form. We do not know its surface temperature. We do not know its reflectivity. We do not know whether it has plate tectonics, volcanic activity, or any form of internal geological processes. Even its age is uncertain. Since Proxima Centauri may not have formed alongside the Alpha Centauri pair, but could have been captured later, it is likely around 5 billion years old. But that estimate is not precise. This list of unknowns is not a failure of science. It reflects the reality of studying a planet detected through indirect methods, where we can measure motion and mass, but not the planet itself. Every exoplanet found purely through radial velocity shares these same limitations. What makes Proxima B unusual is not how much we do not know, but how that uncertainty contrasts with public expectation. Because it is so close, there is a natural assumption that we understand it in detail. Because it lies in the habitable zone, it is often assumed that we can assess its habitability. Because its mass is similar to Earth, it is often imagined to be Earth-like, but proximity creates an illusion of familiarity that the data does not support. There is a certain irony in this. Proxima B is the closest known exoplanet to Earth, yet it does not transit its star. And that single geometric detail means that the one world where detailed study would matter most, where every piece of atmospheric information would carry enormous significance, is also the world where our most powerful tools cannot be used. If Proxima B were to pass in front of its star, the James Webb Space Telescope could already be studying its atmosphere in detail. Using transmission spectroscopy, scientists could search for water vapor, oxygen, ozone, methane, carbon dioxide, and many other molecular signatures. Within just a few years, we might have a meaningful assessment of whether its atmosphere could support conditions similar to habitability. There might even be early hints, however tentative, of biological processes. But that is not the situation we face. What we have instead is a minimum mass and an orbital path. The most significant exoplanet in the sky is also one of the least accessible. This does not make detailed study impossible, but it does make it far more difficult and far slower. One possible approach is direct imaging, attempting to block out the star's light and capture the faint signal reflected or emitted by the planet itself. In theory, this can work. In practice, it is extremely challenging. Proxima B orbits so close to its star that, from Earth, the apparent separation between the two is incredibly small. At present, no instrument can resolve them as separate objects. Future technologies may change this. The Ristretto spectrograph, a high-precision instrument under development for the Very Large Telescope, with deployment expected around 2030, has been designed with targets like Proxima B in mind. Simulations published in 2025 suggest that Ristretto could detect the planet through reflected starlight with around 55 hours of observation, and might even search for signatures of oxygen or water after roughly 85 hours. If these projections hold true under real observing conditions, it could provide the first meaningful constraints on the planet's atmosphere within the next decade. Beyond that, the Extremely Large Telescope, currently being constructed in Chile with a primary mirror nearly 40 meters across, is expected to push these capabilities even further. Planned instruments, including advanced spectrographs and planetary imaging systems, are being developed specifically to study rocky planets around nearby stars. Proxima B is one of the key targets for these future observations. However, these technologies are still years away, and their success depends on solving technical challenges that have not yet been fully overcome. Even in the most optimistic case, A clear understanding of Proxima B's atmosphere is likely to emerge only in the late 2020s or into the next decade. Until then, the closest known exoplanet to Earth will remain a world defined more by possibility than by certainty. Its mass has been measured, its orbit has been mapped, everything else is built on layers of inference. Models built upon models. Assumptions resting on other assumptions. The planet itself is real, but its true nature remains unknown. But even if future instruments eventually show that Proxima B has an atmosphere, even if they detect water vapor, oxygen, or other intriguing signatures, a deeper issue remains, one that no telescope can resolve from a distance of more than 4 light-years. A planet's atmosphere does not exist on its own. It is shaped continuously by the star it orbits, and that star is nothing like our Sun. It is not even a quieter version of it. Proxima Centauri is among the most active stars in our local region of space, and its behavior may dominate every other factor in determining whether its planets could be habitable. By comparison, our Sun is relatively stable. It produces solar flares, coronal mass ejections, and occasional bursts of energetic particles that can interfere with satellites and create auroras near the poles. But these events are manageable. Earth orbits at a distance of about 93 million miles, protected by a dense atmosphere rich in nitrogen and oxygen, along with a global magnetic field that deflects much of the solar wind. When the Sun becomes active, we see light in the sky. When Proxima Centauri becomes active, its planets are directly exposed to intense radiation. The difference between these two stars is not just a matter of brightness or temperature. It comes down to their internal structure. Our Sun is a G-type main sequence star with a layered interior. Energy generated in the core moves outward through a radiative zone, where photons can take hundreds of thousands of years to reach the outer layers. Above that lies a convective region, where hot material rises and cooler material sinks, carrying energy to the surface. The radiative zone below acts as a stabilizing layer, separating the core from the turbulence above. As a result, the Sun's magnetic activity follows relatively regular cycles. Sunspots appear and fade over roughly 11 years. Flares occur, but the overall energy output remains stable. Proxima Centauri operates under very different conditions. As a small M-type red dwarf, it lacks a radiative zone entirely. Its interior is fully convective, meaning that motion occurs throughout the entire star, from core to surface. Hot plasma rises, cooler material sinks, and the whole structure is in constant motion. This has important consequences for how magnetic fields form. In stars like the Sun, the boundary between radiative and convective layers helps organize magnetic fields into more stable patterns. In Proxima Centauri, there is no such boundary. Magnetic fields are generated throughout the entire star, making them stronger, more complex, and more unstable. They twist, tangle, and build up energy until they suddenly release it. These releases are stellar flares. All stars with convective layers produce flares, including our Sun. But Proxima Centauri produces them far more frequently and with much greater intensity. In March 2025, a study led by Kiana Burton and Meredith McGregor presented one of the most detailed analyses of Proxima Centauri's flare activity at millimeter wavelengths. Using the Atacama Large Millimeter Array in Chile, they examined 50 hours of observations and identified 463 individual flare events. That is roughly one flare every 6.5 minutes. Each event lasted only a few seconds, typically between 3 and 16 seconds, but released significant energy, ranging from about 10 to the 24th to 10 to the 27th ergs. These are not minor fluctuations, but rapid and energetic bursts driven by magnetic instability within the star. These were not minor variations. They were intense magnetic eruptions, releasing energy across the entire electromagnetic spectrum, from radio waves to visible light, and into ultraviolet and X-rays, accompanied by streams of high-energy charged particles known as stellar energetic particles. The ALMA observations were particularly important because emission at millimeter wavelengths reveals aspects of flare physics that other wavelengths cannot capture. When particles are accelerated during magnetic reconnection event, they spiral along magnetic field lines and produce synchrotron radiation in the radio and millimeter range. This radiation provides a direct window into the population of accelerated particles, the same particles that, if they reach a planetary atmosphere, can drive chemical breakdown and gradually strip it away. The ALMA study was the first to map how often flares occur on an M-dwarf star at these wavelengths. What it revealed was striking. Smaller flares happen constantly, and the energy distribution follows a power law. This means that while the largest flares are less frequent, the combined effect of countless smaller events creates a near-continuous bombardment rather than occasional disturbances. McGregor summarized the central issue in direct terms. Our sun does not strip away Earth's atmosphere, she explained, because our planet is protected by a dense atmosphere and a strong magnetic field. But Proxima Centauri produces far more energetic flares, and we already know that rocky planets exist within its habitable zone. The question is what those flares are doing to their atmospheres. Are they gradually altering the chemistry, or removing the atmosphere entirely? This is not a theoretical concern. A previous multi-wavelength campaign recorded the most powerful flare ever observed from Proxima Centauri. On May 1, 2019, the star's ultraviolet output increased by a factor of 14,000 within seconds. That event was roughly 100 times more energetic than the strongest flares produced by our sun. And importantly, it may not have been unusual. Observations suggest that events of this scale could occur repeatedly. The 2025 ALMA results reinforced this view, showing just how dense and frequent flare activity is across timescales and energy ranges that had not been fully explored before. Now consider the implications for Proxima B. The planet orbits at a distance of only 0.048 astronomical units, roughly 7 million kilometers from its star. By comparison, Mercury orbits at about 58 million kilometers, around 8 times farther away. Proxima B is extremely close to its star. So close that each flare, each burst of particle, and each surge of ultraviolet radiation reaches it with very little reduction in intensity. Radiation intensity follows the inverse square law. If the distance doubles, the intensity drops by a factor of 4. At Proxima B's distance, the environment during a major flare is not simply harsh. By Earth standards, it would be extreme. High-energy ultraviolet radiation from these flares can break apart atmospheric molecules, altering or destroying them at a fundamental level. Water vapor can be broken apart into hydrogen and oxygen under intense radiation. The hydrogen, being very light, can escape into space with relative ease. The oxygen may also be lost, or it may react with surface materials and become locked into rocks. In either case, the original water is effectively gone. If ozone is present, it can be destroyed by ultraviolet radiation. Without that protective layer, even more ultraviolet light reaches deeper into the atmosphere or down to the surface, accelerating further chemical breakdown. Carbon dioxide can be split into carbon monoxide and atomic oxygen. Nitrogen can be stripped away from the upper atmosphere by energetic particle impact. With each flare, a small part of the atmosphere is lost or altered. Over long periods of time, the cumulative effect could be severe. To understand the scale, it helps to compare this with Earth. Our planet receives ultraviolet radiation from the sun at relatively low levels, and the ozone layer absorbs most of the most harmful wavelengths before they reach the surface. In its quiet state, the sun produces X-ray emissions on the order of 10 to the 27th erg per second. Proxima Centauri, although much dimmer in visible light, can match or even exceed this level of X-ray output because of its far stronger magnetic activity. Even during relatively calm periods, the X-ray flux reaching Proxima B is estimated to be between 60 and 250 times higher than what Earth receives from the sun. That is the baseline. What counts as normal conditions? During a major flare, this radiation can increase by hundreds or even thousands of times within seconds. The powerful event recorded in 2019, where ultraviolet output rose by a factor of 14,000, would have delivered a burst of energy to Proxima B comparable to an event far beyond anything in recorded solar history. On Earth, an event of that magnitude would rapidly overwhelm the ozone layer, trigger large-scale chemical destruction in the upper atmosphere, and expose the surface to ultraviolet radiation capable of damaging DNA within minutes. And that is with Earth's magnetic field and dense atmosphere providing protection. Proxima B may not have either. The particle environment is equally concerning. Large solar events near Earth can deliver proton fluxes on the order of 10 to the 9th to 10 to the 10th particles per square centimeter. At Proxima B's much closer distance, the intensity of similar events could be hundreds of times greater, simply due to proximity. And Proxima Centauri's flares are often far more energetic than those of the Sun. Models suggest that over tens to hundreds of millions of years, this continuous bombardment of high-energy particles could strip away an unprotected atmosphere entirely. Even with a magnetic field comparable to Earth's, the atmosphere would still undergo constant chemical disruption. Nitrogen oxides formed during particle interactions could repeatedly break down ozone. Water vapor in the upper atmosphere would continue to be dissociated. The atmosphere would not disappear all at once, but would instead erode gradually, layer by layer. Even in more optimistic scenarios, where some form of atmosphere remains, the radiation environment at the surface presents another challenge. Ultraviolet wavelengths that are especially damaging to organic chemistry would penetrate much more easily than they do on Earth, reaching levels that could significantly alter or limit biological processes, especially if ozone cannot be maintained against continuous photochemical destruction. Biological molecules such as DNA and RNA become extremely vulnerable to UVC radiation. On Earth, these wavelengths are almost entirely absorbed by the ozone layer before they can reach the ground. On Proxima B, without a stable ozone shield, the surface would be exposed to intense, biologically damaging radiation during flare events, and possibly even during quieter periods. Any life exposed on the surface would experience DNA damage at levels far beyond anything found on Earth. This does not necessarily rule out life altogether, but it does restrict where life could exist. Subsurface environments, deep oceans, or organisms protected by rock, ether, or specialized pigments that absorb ultraviolet light could offer some degree of protection. Some researchers have also pointed out that the radiation from Proxima Centauri may not be well suited for oxygen-producing photosynthesis, the process used by plants and cyanobacteria on Earth. However, alternative forms of photosynthesis that rely on longer wavelengths might still be possible. One study suggested that the overall biological productivity of such a system could be only around 20% of what we see on Earth. If life does exist there, it would likely be confined to limited, sheltered regions rather than spread across a broad, sunlit surface. The familiar image of forests, oceans, and open landscapes, often implied by the term Earth-like, is unlikely to match the conditions of this world. Any life on Proxima B would probably exist out of sight, beneath the surface, underwater, or shielded by layers of rock or ice, avoiding the very radiation that defines its position within the habitable zone. There is a certain irony in this. The same stellar energy that places the planet in the habitable zone may also make its surface environment hostile. Beyond the repeated flare activity, there is another constant factor to consider: the stellar wind. This is the steady flow of charged particles emitted by the star between flare events. It represents a continuous pressure that a planet must resist at all times, not just during extreme outbursts. Estimates suggest that Proxima Centauri's stellar wind could exert between 4 and 80 times the pressure experienced by Earth from the Sun. If Proxima B lacks a sufficiently strong magnetic field, this wind could gradually erode its upper atmosphere through a process known as sputtering, where energetic particles physically knock atmospheric molecules into space over time. This is not a sudden event, but a slow, continuous loss. Whether Proxima B has a magnetic field is one of the most important unanswered questions. On Earth, the magnetic field is generated by the movement of molten iron within the outer core, driven by internal heat and organized by the planet's rotation. This process, known as the dynamo effect, depends on both internal structure and rotational speed. Earth completes one rotation every 24 hours. Proxima B, if it is tidally locked, would rotate once every 11.2 days. A slower rotation could weaken the dynamo process and reduce the strength of any magnetic field. Some models suggest that a planet of similar mass could still generate a magnetic field under these conditions, though likely weaker than Earth's. Others propose that tidal heating from the nearby star might help maintain a molten core and sustain magnetic activity. However, these ideas remain theoretical. We do not yet have observational evidence to confirm whether Proxima B possesses a magnetic field. Without one, its atmosphere would be largely exposed to both stellar wind and flare-driven radiation. Even with a magnetic field, it would need to be strong enough to withstand conditions far more intense than those experienced by Earth. Different models offer different outcomes, depending on assumptions about the star's magnetic structure, the strength of the stellar wind, and the internal properties of the planet itself. Some scenarios suggest that the magnetopause, the boundary where a planet's magnetic field pushes back against the stellar wind, could be compressed so close to the surface that it offers very limited protection. Other models, however, indicate more favorable configurations where the shielding remains more effective. This wide range of outcomes reflects how little we truly know about the planet's interior structure and surface environment. Tidal locking adds another layer of complexity. A planet in a 1-to-1 spin orbit resonance keeps the same side always facing its star. One hemisphere remains in constant daylight, while the other is locked in permanent night. This creates an extreme contrast in temperature between the two sides, potentially reaching hundreds of degrees depending on the atmosphere and how efficiently heat is transported. Without an atmosphere, the day side would become intensely hot, while the night side would cool to temperatures approaching those of deep space. Even with an atmosphere, the behavior becomes unusual. Climate models show that winds can redistribute heat from the illuminated side to the dark side, with the effectiveness depending on atmospheric thickness and composition. A dense atmosphere with efficient circulation could produce a more balanced climate, with the day side warm enough for liquid water and the night side cold but not excessively so. However, there are failure cases. A thin atmosphere may begin to collapse on the night side, where temperatures drop low enough for gases to freeze and settle as surface ice. Carbon dioxide would likely condense first, followed by other components. As the atmosphere thins, its ability to move heat decreases, which in turn accelerates further collapse. This runaway process is a serious possibility for planets orbiting red dwarfs, especially those with weaker greenhouse effects than Earth. Even if the atmosphere remains intact, the permanent contrast between day and night produces weather systems unlike anything we experience. Models predict strong upward airflow at the substellar point, where heating is most intense, and descending air on the night side, forming a global circulation pattern. Fast-moving equatorial winds could develop, transporting heat from the day side toward the night side at high altitudes. Clouds would likely form predominantly over the illuminated region, increasing reflectivity and reducing the amount of energy absorbed. The interaction between these processes is complex and highly dependent on model assumptions. Different atmospheric compositions lead to different circulation behaviors. Variations in rotation, such as a 3-to-2 resonance instead of a 1-to-1 lock, would produce entirely different temperature patterns. The climate of Proxima B is not a single outcome, but a broad range of possibilities, and we currently lack observations to constrain them. Some modeled scenarios are detailed enough to highlight just how unfamiliar this world could be. One of the most discussed possibilities is known as the eyeball planet. In this scenario, if Proxima B is tidally locked with a moderate amount of water and a sufficiently thick atmosphere, the point directly facing the star could host a circular region of open ocean, surrounded by a ring of ice that stretches into the dark hemisphere. Seen from above, the planet would resemble a large eye directed toward its star. The central ocean might be warm enough to sustain liquid water, but it would also be exposed to constant ultraviolet radiation. Surrounding it, the ice layer could extend for great distances, forming a frozen hemisphere where temperatures might fall to -80 or even -100 degrees Celsius, depending on how effectively heat is redistributed. Other models describe what researchers sometimes call lobster-shaped habitable regions. In these cases, the atmosphere can move heat beyond the point directly facing the star, but not efficiently enough to warm the entire dayside evenly. Instead, two roughly symmetrical zones of moderate temperature extend outward along the equator on either side of the substellar point, forming shapes that resemble open claws when viewed from above. Outside of these regions, conditions become too extreme. Temperatures across most of the planet are either too high or too low for liquid water. If habitability exists at all, it is limited to these narrow bands where conditions briefly align. A third possibility involves atmospheric collapse. If the atmosphere is relatively thin, dominated by carbon dioxide, and lacks sufficient greenhouse warming, temperatures on the night side could fall below the point where carbon dioxide condenses, around -78 degrees Celsius, under typical pressure. In that case, carbon dioxide would freeze into dry ice across the dark hemisphere, gradually thinning the atmosphere. This leads to a feedback cycle. As the atmosphere becomes thinner, it loses its ability to transport heat. This makes the night side even colder, causing more gas to freeze out, which further reduces atmospheric pressure. Over time, the system could settle into a state where only a thin, uneven atmosphere remains over the warmest parts of the dayside, while the rest of the planet is covered in frozen carbon dioxide under permanent darkness. Such a world could still technically lie within the habitable zone, but it would resemble an environment like Antarctica, where life is possible only for highly specialized organisms and where complex ecosystems struggle to exist. Each of these scenarios is consistent with what we currently know about Proxima B. Each is physically plausible given different assumptions about atmosphere and composition, and none of them resemble Earth. A tidally locked Proxima B, whatever its exact state, would likely be a planet defined by extremes, sharp gradients, and asymmetries unlike anything in our solar system. The familiar image of a blue and green world, with oceans and continents spread beneath a stable sky, is almost certainly misleading here. Even the most optimistic models describe a planet that would feel profoundly unfamiliar to human experience, and even the assumption of tidal locking is not fully certain. While a 1-to-1 resonance is the most likely outcome for a planet orbiting this close to a red dwarf, other configurations remain possible. If Proxima B has even a slight orbital eccentricity, it could instead be captured in a 3-to-2 resonance, similar to Mercury's orbit around the Sun. In such a state, the planet would rotate 3 times for every 2 orbits, allowing all regions of the surface to experience both day and night. Though in a complex and uneven cycle, this configuration would soften the extreme temperature contrast seen in a fully locked planet, but it would introduce another factor: tidal heating. As the planet's shape flexes slightly along its orbit, internal friction could generate heat, potentially driving volcanic activity or influencing the generation of a magnetic field. Recent work has added further complexity to this picture. A study published in 2023 explored a regime known as spin-orbit resonance transitions, where planets may shift between different rotational states over timescales ranging from decades to hundreds of thousands of years. Depending on their internal structure and the architecture of the system they belong to, within this framework, Proxima B may not be locked into a single stable rotation state at all. Instead, it could shift between different resonances over time, undergoing significant changes in how it spins, and with that, major shifts in its climate. These dynamics depend strongly on the planet's orbital eccentricity, which remains poorly constrained. Radial velocity data places an upper limit somewhere between about 0.25 and 0.35, but the true value could be much lower. Or it could vary due to gravitational interactions with Proxima D or other unseen planets in the system. There is also another layer to the habitability question that is often overlooked, one that unfolds over time. Proxima Centauri, like other red dwarfs, passed through an extended early phase during which it was far more luminous than it is today. Young red dwarfs begin brighter and hotter as they contract towards stability. During that stage, the habitable zone was located farther from the star than it is now. A planet at Proxima B's present orbit would have been well inside the inner edge of that zone, receiving significantly more energy than it does today. For Proxima Centauri, models suggest that this intense phase may have lasted up to 180 million years. During that time, Proxima B would have been exposed to levels of radiation capable of triggering a runaway greenhouse effect. This process begins when a planet absorbs enough energy to evaporate its surface water into the atmosphere. Water vapor then acts as a greenhouse gas, trapping heat and driving temperatures higher. As temperatures rise, more water evaporates, which leads to further warming. The cycle reinforces itself until nearly all surface water exists as vapor. In the upper atmosphere, ultraviolet radiation breaks apart these water molecules. Hydrogen escapes into space, while oxygen is either lost or reacts with surface materials. Over time, the planet can lose its water entirely. This is believed to be what happened to Venus. Early in its history, Venus may have had liquid water, but increasing solar energy pushed it beyond a critical threshold, and the resulting runaway greenhouse removed that water permanently. Proxima B may have experienced something similar. If it began with a significant amount of water and spent hundreds of millions of years under intense radiation, it could have lost most or all of that water long before conditions became more moderate. By the time the habitable zone moved inward to its current position, the planet might already have been dry. A world at the right distance, but shaped by the wrong history. This is not certain. The delivery and retention of water on planets is complex. Impacts from comet, outgassing from the interior, and later delivery of volatile materials could potentially restore some of what was lost. Some models indicate that Proxima B may have preserved a portion of its water through the early pre-main sequence phase, particularly if it began with a very large reservoir, perhaps several times the volume of Earth's oceans. But other studies, including work by Arapetian and colleagues in 2017, suggest a far more extreme outcome, where the planet's atmosphere could be stripped away entirely within 10 million years under intense stellar wind and ultraviolet exposure. These estimates depend heavily on initial conditions, the starting mass of the atmosphere, composition, and whether a magnetic field was present during that early, volatile period. The most honest conclusion is that we simply do not know whether Proxima B entered the habitable zone as a water-rich world or a dry one. We do not know if any water it once had survived the violent early phase of its start. This leads to a difficult synthesis. Proxima B orbits a star that can produce hundreds of flares within a single observation window. It sits roughly 20 times closer to its star than Earth does to the Sun. It is likely tidally influenced, creating climate patterns with no true equivalent on Earth. It may lack a magnetic field strong enough to shield its atmosphere from continuous particle exposure. It likely spent its first 180 million years under a brighter, more intense version of its star. During that time, it may have lost its atmosphere, its water, or both before conditions became more stable. And each of these uncertainties is compounded by the fact that we currently have no direct way to confirm or rule them out. The flare environment alone is enough to raise serious questions. A single large flare from Proxima Centauri can deliver more ultraviolet energy to Proxima B in seconds than Earth receives from the Sun over the course of an entire day. The cumulative effect of countless smaller flares, occurring repeatedly, as suggested by observational data, creates a radiation environment unlike anything found in our solar system. As McGregor noted when discussing the implications of these findings, if life does exist on the planet nearest to Proxima Centauri, it would have to be very different from anything we know on Earth. A human being placed there would not survive easily. This observation captures the broader emotional arc of the Proxima B story. When it was first announced in 2016, it was framed as a source of optimism. The nearest star appeared to host an Earth-mass planet within its habitable zone, but with each new study, the picture has become more complex. The star is highly active. The planet may be dry. Its atmosphere may be gone. Its climate could be extreme. And the lack of a transit prevents detailed characterization. Rather than becoming more promising, the picture has grown more uncertain. And that uncertainty is itself revealing, because the early narrative was built on hope that the available science has not yet confirmed. None of this proves that Proxima B is uninhabitable. Science depends on evidence. And in this case, the evidence is simply incomplete rather than negative. It remains possible that the planet retained enough water through its early history to sustain ocean. It is possible that a dense atmosphere could endure the constant flare activity through ongoing volcanic replenishment. It is possible that a magnetic field exists and provides enough shielding to preserve that atmosphere. It is even possible that unfamiliar forms of life could survive under conditions that would be fatal to every known organism on Earth. All of these scenarios remain consistent with what we currently understand, which is very little about the planet's true nature. The issue is not that Proxima B has been proven to be hostile. The issue is that the environment created by its star makes hostility the most likely baseline, and we have no direct way to test that assumption. This is the reality that future instruments will have to face, not a world waiting to confirm our expectations, but one that requires every piece of knowledge to be earned through observations of exceptional difficulty around a star that actively obscures the signals we need. And even if those instruments succeed, even if Ristretto detects reflected light, and the extremely large telescope begins to constrain the atmosphere, there remains another barrier. Amore fundamental one. It is not a limitation of science, but of physics itself. It is the distance. 4.2 light-years. A number that once felt encouragingly small begins to feel very different when we consider what it actually represents. Say it aloud and it seems manageable. A modest number paired with a familiar unit. It fits easily into conversation. Almost like a distance one might travel in a long journey. But in reality, 4.2 light-years is about 25 trillion miles. Written out, that is 25 followed by 12 zeros. If you were to drive continuously at highway speed, without ever stopping, the journey would take around 48 million years. At the speed of a commercial aircraft, it would still take roughly 5 million years. These comparisons sound absurd, and they are meant to be, because interstellar distances resist human intuition. We are used to thinking in miles, not trillions of them. The fastest object ever built by humanity, the Parker Solar Probe, can reach speeds of over 430,000 miles per hour at its closest approach to the Sun. At that speed, it could travel between major cities on Earth in seconds, or circle the planet in just a few minutes. Yet even at that velocity, reaching Proxima Centauri would take around 6,600 years. For perspective, recorded human history spans only about 5,000 years. The Voyager 1 spacecraft, launched in 1977, and now the most distant human-made object, travels much more slowly, at around 38,000 miles per hour. At that speed, the journey would take approximately 73,000 years. Modern humans have existed for roughly 300,000 years. Voyager would require a significant fraction of that entire time span to reach the nearest star. These are not challenges that can be easily solved with incremental improvements in technology. They reflect a deeper reality. The gap between interplanetary and interstellar travel is immense, separated by factors of 100,000 or more. Mars, at its closest, lies about 50 million miles from Earth. Proxima Centauri lies about 25 trillion miles away. That is roughly 500,000 times farther than Mars at its closest approach. We have sent robotic missions to Mars. We have landed there, driven across its surface, and even flown a small helicopter through its thin atmosphere. But Mars is, in comparison, a short walk across a familiar landscape when set against the distance to the nearest star. The propulsion systems that make planetary exploration possible, chemical rockets, ion drives, gravity assists, were designed for a solar system spanning billions of miles, not the vast scales between stars. The most ambitious idea for reaching Proxima Centauri remains the breakthrough starshot concept. Introduced around the time of Proxima B's discovery, in principle, the physics work. Accelerating a tiny probe to about 20% of the speed of light using a powerful laser array is consistent with known laws. But turning that concept into reality reveals the true challenge. The required laser system would need to generate around 100 gigawatts of power, comparable to the output of entire nations, focused into a beam precise enough to push a sail only a few meters wide and incredibly thin. That sail would have to endure extreme acceleration forces, thousands of times Earth's gravity, over several minutes, without tearing apart or deforming. The onboard instruments, weighing only milligrams, would then need to survive decades in interstellar space, exposed to dust, radiation, and near absolute zero temperatures. Once it reached the system, it would have to collect meaningful data during a flyby lasting only minutes, and then transmit that information back to Earth across 4 light-years, using a power source no larger than a small battery, with extraordinary precision. Each of these steps pushes the limits of current technology. No full system has been tested, no launch timeline has been established, and even if every challenge were solved, the mission would still be limited. What arrives at Proxima Centauri would not be an orbiter or a lander. It would not remain to study the planet over time. It would be a tiny probe moving at around 60,000 kilometers per second, passing through the system in a brief instant, capturing whatever data it can in that short window. At such speed, some measurements are possible. It could sample the magnetic environment, detect charged particles, and perhaps capture a rough image of the planet if everything aligns perfectly. But it could not answer the most important questions. It could not land. It could not analyze the atmosphere in detail. It could not study surface chemistry or determine whether the planet hosts life. The very speed that makes the journey possible also limits what can be learned. The probe arrives quickly, but it barely has time to observe. If we imagine the encounter from the probe's perspective, the scale becomes even clearer. At 20% of the speed of light, the distance between Earth and the Moon would be crossed in just a few seconds. The probe would enter the Proxima Centauri system and move from its outer regions to the orbit of Proxima B in only a matter of minutes. The planet itself, even if the probe passes within a few thousand kilometers, would remain in view for only a few brief seconds. In that short interval, any onboard camera would need to detect the planet through the glare of its star, orient itself, capture an image, and store the data. There would be no second opportunity. There is no looping back for another pass. At speeds approaching 60,000 kilometers per second, the probe would rush past the planet before any meaningful course correction could even be attempted. The encounter would be over almost as soon as it begins. Whatever data is collected in that fleeting moment would then need to be transmitted back across 4.2 light-years. Using a laser or radio system powered by extremely limited onboard energy, the signal, weakened across trillions of miles by the inverse square law, would be extraordinarily faint, barely detectable even by the most sensitive receivers on Earth. And once sent, it would still take more than 4 years to arrive. This is not exploration in the way we have come to understand it. When Voyager passed Jupiter and Saturn, it spent hours and days within observational range, sending back thousands of images and measurements that reshaped our understanding of those worlds. When New Horizons reached Pluto, its closest approach lasted nearly a full day, producing data that scientists continue to analyze years later. A probe sent to Proxima Centauri would have minutes at best, and only seconds during its closest pass. Its instruments would be measured in milligrams rather than kilograms. The total return might consist of a few data points, perhaps a single indistinct image, transmitted at extremely low data rates. It could become the most expensive image ever captured, and yet show little more than a faint point of light against darkness. Useful, Perhaps, but unlikely to answer the questions that matter most. Whether Proxima B has an atmosphere, liquid water, or life. This is the paradox of Proxima B's proximity. 4.2 light-years is close enough to inspire mission concepts. Close enough to motivate engineers and physicists to begin serious calculations. Close enough that it feels, at least in principle, within reach of future generations. But it is not close enough to allow the kind of detailed exploration that would resolve its mysteries. The missions we can realistically design today are flybys, not long-term studies. They offer brief glimpses, not sustained observation. They would add fragments of information, not complete answers. And they would require decades to plan, build, launch, travel, and return their signals. By the time such a mission delivers its results, telescopes on Earth and in space may already have advanced to the point where they can extract more information from a distance than a fast-moving probe could gather up close. The path forward through observation is real, but it is gradual. The Ristretto instrument, expected to be installed on the Very Large Telescope around 2030, represents one of the most focused, near-term efforts to study Proxima B from Earth. Its design combines advanced adaptive optics with high-resolution spectroscopy, aiming to separate the faint reflected light of the planet from the overwhelming brightness of its host star. Simulations published in 2025 suggest that Ristretto may be capable of detecting this reflected signal and placing constraints on the planet's atmosphere within a realistic number of observation nights. Those projections are ambitious for a ground-based instrument, and they rely on performance levels that have not yet been proven under real observing conditions. Atmospheric turbulence, instrumental limitation, and the star's own flare activity will all add layers of difficulty. Ristretto may achieve its goals, or it may fall short. We will only know once it is fully built, installed, and tested against the actual light arriving from Proxima Centauri at the telescope. The extremely large telescope, currently under construction in Chile, will be the most powerful ground-based observatory ever created, with a primary mirror measuring 39 meters across. Among its planned instruments are Andes, a high-precision spectrograph designed for studying rocky exoplanets, and the Planetary Camera and Spectrograph, intended to directly image and analyze planets around nearby stars. Proxima B is a key target for both. With a light collecting capability far greater than existing telescope, the ELT offers a significant advantage in detecting faint planetary signals hidden within the brightness of a star. If any ground-based system can begin to unravel the nature of Proxima B, it is likely to be this one. Even so, full scientific operations are not expected until the late 2020s, and the most challenging observations will require years of calibration and refinement before they can be attempted reliably. Space-based options exist in theory, but not yet in finalized form. A large telescope equipped with a coronagraph or starshade could block out the light of Proxima Centauri and directly observe the planet itself. One proposed mission, the Habitable Worlds Observatory, is intended to study Earth-sized planets in the habitable zones of nearby stars. Proxima B would be an obvious target, but for now, the mission remains in an early conceptual stage. It has not been fully approved, funded, or scheduled. Even under optimistic assumption, such a mission would not launch until the late 2030s or beyond. This means the closest known exoplanet may remain only partially understood for decades. Proxima B was discovered nearly 10 years ago. Since then, it has been the focus of extensive research, climate simulations, atmospheric modeling, studies of magnetic fields, stellar wind interactions, and even mission concepts. An entire branch of exoplanet science has, in many ways, formed around this single world, and yet, despite all of this effort, the most basic questions remain unanswered. Does it have an atmosphere? We do not know. Does it hold water? We do not know. Is its surface capable of supporting life? We do not know. Could life exist there at all? We do not know. The planet is just over 4 light-years away. And still, We cannot truly read it. The nearest potentially meaningful world remains closed to us, like a locked box, and the key lies in instruments that have yet to be built. There is something deeply unsettling about that reality. When a potentially habitable planet is found hundreds of light years away, the difficulty of studying it feels expected, almost natural. Of course, when a planet lies hundreds of light years away, we accept the limitation almost instinctively. Our tools are not built for that scale, and the universe, in its vastness, places those worlds far beyond reach. But Proxima B unsettles that acceptance. It is not hundreds of light years away. It is just over 4. It feels close, almost unreasonably close. It is the nearest planet around the nearest star, orbiting within a region where liquid water could exist, with a mass strikingly similar to Earth's. By every intuitive measure, it feels like a place we should be able to understand, perhaps even visit, and yet, we cannot. The distance that once seemed reassuring has revealed itself to be just large enough to defeat every method we currently possess. 4.2 light-years is a boundary, not a bridge. It is close enough to observe, but too far to touch, close enough to imagine, but too distant to truly know. This tension between nearness and inaccessibility is not only a technical challenge, it carries a deeper, more human weight. Proxima B occupies a unique place in our imagination because it feels personal. When we speak about planets orbiting distant stars, dozens or hundreds of light years away, the conversation remains abstract. Those worlds become entries in a catalogue, data points that inform our understanding of the galaxy. They expand our knowledge, but they do not feel like destinations. Proxima B does. Its proximity creates a kind of quiet intimacy. Even those unfamiliar with astronomy have heard its name. They know it is the closest. They know it might be habitable, and in some subtle way, they feel connected to it, as if it represents the next step outward. But the science tells a different story. It describes a world defined by uncertainty, orbiting a star defined by instability, at a distance that is deceptively vast. The phrase nearest habitable zone planet carries an implication that does not hold under closer examination. Nearest suggests something within reach. Habitable zone suggests a place where life could exist. Planet suggests a world with knowable properties. In reality, nearest means a gulf of space that cannot yet be crossed. Habitable zone refers only to a range of energy, not to actual conditions. Planet means an object inferred through motion, with no confirmed size, no measured density, no direct evidence of an atmosphere, and no clear understanding of its surface. What makes Proxima B so compelling is not its distance alone, but the contradiction it represents. It is close enough to awaken our hopes of finding another Earth, yet distant and uncertain enough to deny us any clear answer. It becomes a kind of mirror, reflecting our expectations about the universe, while withholding the reality behind them. We imagine oceans, skies, perhaps even life. We wonder whether another world like ours might exist just beyond our reach. Proxima B sits at exactly the threshold where those ideas feel almost real, just within the edge of possibility. And almost is the key word here. Almost reachable, almost understandable, almost habitable, but never fully confirmed. There is a concept in psychology known as the uncanny valley, a sense of unease that emerges when something appears almost human, yet not quite. Proxima B seems to occupy a similar space, but on a cosmic scale, at first glance, it resembles the kind of world we have been searching for. Earth-like in mass, located in the habitable zone, orbiting the nearest star. But as we look closer, the resemblance begins to break apart. The star is unstable, the orbit may be locked, the atmosphere could be gone, any early water may have been lost billions of years ago, and the planet does not transit, leaving its atmosphere hidden from our most powerful tools. The closer we examine it, the more that initial promise gives way to uncertainty, and perhaps even hostility. It is not an Earth twin. It is not a confirmed habitable world. It is not a destination waiting to be explored. It is a question. one that we do not yet have the means to answer. And perhaps that is what makes Proxima B so important. Not what it is, because that remains unknown, but what it reveals about the tension between human expectation and cosmic reality. The moment we discovered planets beyond our solar system, we began to imagine finding ourselves reflected among the stars. Another Earth, another place where life might begin again, another home. Proxima B seemed, for a moment, to bring that idea within reach. A rocky world in the habitable zone of the nearest star. It felt almost too perfect. But the universe does not shape itself around human hope. Instead, it presents a more complicated picture. A nearby world, but one exposed to a star that may strip its atmosphere. An orbit that hides its most important features from observation. A distance that resists even our fastest technology. And a level of uncertainty that may persist for decades. Proxima B may be a lifeless world. Or it may be something far more remarkable. We simply do not know. And that uncertainty extends beyond a single planet. Red dwarfs are the most common stars in the galaxy. Many of them are active. Many host rocky planets in their habitable zones. If Proxima B is representative, if the effects of stellar flares, tidal locking, early radiation, and atmospheric loss are typical, then the implications are much larger. It would suggest that the most common type of potentially habitable world may also be the most compromised, that the planets we can detect most easily, those around red dwarfs with short orbital periods and strong signal, may also be the least likely to support life as we understand it. In that case, the galaxy could be filled with worlds like Proxima B, planets that appear promising at first glance, but reveal deeper challenges when examined more closely. This is not a conclusion, but it is a possibility that has become difficult to ignore, and it leads directly into one of the oldest and most unsettling questions in astronomy. If habitable zone planets around red dwarfs are as common as current estimates suggest, numbering in the tens of billions, and if many of them face the same challenges as Proxima B, then the galaxy may not be filled with welcoming environments. It may instead be filled with worlds that meet the initial criteria for habitability: the right mass, the right orbit, the right energy from their star, and yet remain fundamentally inhospitable beneath the surface, but fail when examined more closely. Because the limiting factor is not the planet, but the star it depends on, this carries deeper implications for the Fermi paradox. The long-standing question of why we have not yet detected signs of extraterrestrial intelligence despite the apparent abundance of potentially habitable worlds. One explanation has always been that true habitability is far rarer than it appears at first glance. Proxima B offers a possible mechanism behind that idea. The most common stars in the galaxy produce the most common habitable zone planets. Yet those same stars may actively prevent habitability through persistent radiation, atmospheric erosion, and tidal effects that do not occur around stars like our Sun. If this pattern is widespread, then the silence of the universe becomes less mysterious. It becomes expected. The galaxy may appear rich in opportunity, but beneath the surface, many of those environments could be fundamentally hostile. Worlds that seem promising at a distance may reveal themselves to be chemically or physically unforgiving when examined more closely. And yet, there is another possibility. Perhaps Proxima B has endured. Perhaps a dense atmosphere, continually replenished by volcanic outgassing, has survived despite the constant flare activity. Perhaps a magnetic field, even if weaker than Earth's, provides enough protection to slow atmospheric loss. Perhaps the planet retained enough water, or regained it through later processes, to sustain oceans. Perhaps its atmospheric chemistry has evolved in ways that offer stability against intense radiation. And perhaps, if life exists there, it has adapted to conditions that would be lethal to organisms on Earth, but are simply part of its natural environment. On our own planet, life persists in places once thought impossible, in acidic springs, beneath Antarctic ice, deep within the ocean under immense pressure, and in regions exposed to high radiation. The limits of biology are broader than we once believed. A world that seems extreme to us might still support life adapted to those extremes. We do not know which of these possibilities is true, and for now, we cannot know, not from this distance, not with the instruments we currently have, and not without years, perhaps decades, of further observation. That is the reality of Proxima B that no headline fully conveys. The unsettling truth is not that the planet has been proven barren. A confirmed barren world would be easier to accept. We would acknowledge it and move on. The deeper discomfort comes from the uncertainty itself. Proxima B is close enough to be the most compelling world beyond our solar system, yet unknown enough to be almost anything. From a hidden ocean world to a radiation-stripped desert, it exists within a range of possibilities. At once, a candidate for habitability and a candidate for complete inhospitability, and only observation will eventually narrow that range. Until then, Proxima B remains in a uniquely uneasy position. Not a confirmed hope, not confirmed despair, simply the nearest world that might matter, suspended in the dark, a little over 4 light-years away, offering no clear answer. If we set aside the headlines, the ambitious mission concept, the dramatic narratives, and the easy label of a nearby Earth twin, what remains is something far more honest, and perhaps far more unsettling. We live in a universe where the closest planet that could, in theory, support life orbits a star that repeatedly exposes it to radiation, capable of dismantling the very chemistry life depends on. We live in a universe where that planet's most critical properties remain hidden because of a simple geometric alignment that prevents our most powerful observational techniques from working. We live in a universe where 4 light-years, the smallest distance between stars, still exceeds the reach of every propulsion system we have ever created and every realistic mission we have designed. We live in a universe where the nearest potentially significant world is close enough to capture our imagination, yet distant enough to resist clear understanding for decades. The closest world that could matter is also the one we cannot fully read, cannot physically reach, and cannot easily ignore. It lingers in our thinking, not because of what we know, but because of what we do not. That is the deeper truth of Proxima B. Not that it is confirmed to be lifeless, and not that it is a hidden paradise. Not even that it holds the answer to whether we are alone, but that it exists at a distance where possibility and limitation overlap, close enough to feel relevant, far enough to remain uncertain. It reminds us that the universe is not arranged for our convenience. It does not place its most important questions within easy reach. Proxima B sits just over 4 light-years away. That is near enough to reshape how we think about our place in the cosmos. But it is not near enough to reveal what is truly there. And that gap, between knowing a world exists and understanding what it is, between detecting it and experiencing it as a place, may be one of the most profound distances in all of science.